Welcome, data engineers. Let's get started on mastering Apache Airflow, the absolute industry standard for scheduling and orchestrating ETL pipelines. Welcome, data engineers. Today, we are mastering Apache Airflow, the absolute industry standard for scheduling and orchestrating ETL pipelines. So, what exactly is Apache Airflow? It is a powerful open-source workflow management platform, initially developed at Airbnb, that allows you to programmatically author, schedule, and monitor your data pipelines. Think of it as the central nervous system of your entire data architecture. Why do we heavily rely on it for our ETL and ELT processes? Primarily because it is completely tool-agnostic, highly extensible, and incredibly scalable. You write your pipelines using pure Python code, which grants you the power to implement complex logic, dynamic task generation, and version control. Instead of relying on rigid, black-box drag-and-drop enterprise tools, Airflow brings software engineering best practices directly into data engineering. The scheduler takes care of dynamically triggering and monitoring tasks based on precise schedules and complex dependency rules, preventing issues caused by invalid or incomplete data. Let's dive deep into the core components. Looking at our first diagram, we see the classic extract, transform, and load process, the ETL pipeline. But notice the central node, the Airflow scheduler. The scheduler doesn't actually process the heavy data itself. Instead, it acts as an orchestrator. It triggers the extract task to pull data from a source, monitors its success, and only then triggers the transform task. Once transformation is complete, it signals the load task to push the refined data into your data warehouse. This separation of orchestration from execution is exactly what makes Airflow so incredibly powerful and scalable for modern data teams. At the very heart of Airflow is the concept of a DG, which stands for Directed Acyclic Graph. A DG is simply your data pipeline represented as a mathematical graph. It contains all your individual tasks arranged in a strictly ordered fashion. Let's break down the acronym. Directed means that the workflow has a specific direction. Execution flows strictly from one task to the next based on defined dependencies. Acyclic is a critical constraint. It means there are absolutely no loops. A task cannot depend on a task that comes after it, because that would create an infinite execution loop, halting your pipeline entirely. When you create a DG file in Python, you're creating an object that holds the metadata for your workflow, like the schedule interval and the start date. Once the DG is defined, Airflow instantiates it at specific points in time, which we call a DG run. Every single time your scheduled interval hits, a new DG run is created, ensuring your data is processed reliably over time. This diagram perfectly illustrates the critical difference between a valid DG and an invalid workflow. On the left, we see a valid directed acyclic graph. Task 1 successfully flows into Task 2, which then branches out in parallel to Task 3 and Task 4. The data flows downstream logically. However, on the right, we see what happens when you introduce a cycle. Task B points to Task C, but Task C points directly back to Task A. This creates an infinite loop. Airflow is strictly designed to prevent this. If you attempt to build a pipeline with a cycle, Airflow will immediately throw a compilation error and refuse to parse the file. Now that we deeply understand the DG structure, let's talk about the exact building blocks, operators, and tasks. In Airflow, a task is simply a unit of work that needs to be done, and an operator is the predefined template used to create that specific task. Think of an operator as a convenient abstraction of the exact logic you want to execute. For example, if you want to execute a Python function, you instantiate a Python operator. If you want to run a bash command, you use a bash operator or a SQL check operator to run data quality checks natively inside a database. Each time you add an operator to your DG script, you are adding a new, distinct task node. A modern best practice in Airflow 2 and 3 is utilizing the TaskFlow API. By simply adding an @task decorator directly above a standard Python function, Airflow automatically converts it into an executing task and intuitively handles passing data between your tasks using XComs behind the scenes. This heavily reduces boilerplate code. Here we can visualize exactly how operators function as abstractions within your Airflow environment. You start with the base operator template concept. Depending on the exact action your ETL pipeline requires, you select a specific operator type from the library. Choosing the Python operator allows you to execute native Python functions, making it perfect for API calls or complex pandas transformations. The bash operator directly executes shell scripts, which is excellent for moving files around the operating system. The SQL operator securely passes queries directly into your data warehouse. You do not need to write connection logic from scratch. The operator handles it all. Scheduling is arguably the most crucial feature for automating massive ETL pipelines. When you define a DG, you must provide a start date and a schedule, which can be a standard cron expression or a preset like at daily. But how does Airflow actually understand time? It relies entirely on data intervals. If you set a daily schedule starting on February 1st, your first DG run technically covers the logical interval from February 1st to February 2nd, and it executes strictly after that interval completes. This brings us to a massive, cost-saving optimization technique, incremental loading. Instead of dropping and reloading an entire massive database table every single day, you utilize Airflow's built-in template variables, specifically data interval start and data interval end. By passing these variables dynamically into your SQL queries or REST API calls using Jinja templating, your pipeline will intelligently fetch and process only the exact delta of data generated during that specific 24-hour window. Let's carefully look at this sequence diagram to understand how the Airflow scheduler interacts with time to execute efficient incremental loads. As time passes in the real world, the scheduler constantly evaluates your DG's defined logical intervals. Once the very first 24-hour interval completes, say, midnight on February 2nd, the scheduler immediately triggers a DG run. Crucially, it injects the execution date parameters directly into your code. Your task uses that exact date to fetch only the data for February 1st. Then, the timeline continues. Once the next 24-hour cycle finishes, a completely new DG run is triggered, passing the new date variables. Creating tasks is only half the battle. Orchestrating their precise execution order is where Airflow's real power shines. We set up dependencies to guarantee mathematically that data is extracted before it is transformed and transformed before it is loaded. In Airflow, we elegantly define this order using bit shift operators, specifically the right shift operator. By simply writing task A right shift task B, we explicitly tell the scheduler that task B is a downstream dependency and absolutely cannot start until task A successfully finishes its execution. For highly advanced enterprise pipelines, we utilize logical branching. The branch Python operator, or the task.branch decorator, allows us to execute a custom Python function that evaluates a specific real-time condition and returns the ID of the exact next task to run. For instance, if a data quality threshold is completely met, the pipeline branches down the success path to load the data. If it fails, it skips the load and branches down a specific alerting path. This flowchart dynamically demonstrates a modern pipeline utilizing task dependencies alongside conditional branching logic. Data is first extracted, and once that is entirely and successfully complete, the transformed data task begins execution. After transformation, we hit a critical decision, note our branch operator. This specific task evaluates the freshly transformed dataset against strict, predefined data quality metrics. Depending on the mathematical result, the pipeline physically alters its execution path at runtime. If the data cleanly passes the check, it flows smoothly down the left branch to be loaded. If the check catches a bad anomaly, the pipeline branches to the right, skipping the load and triggering an alert. Let's do a deep dive into managing temporary resources and ensuring absolute data quality during the ETL process. Modern pipelines frequently involve creating temporary staging tables in a cloud data warehouse, loading raw API data into them, running intense SQL column and table checks, and then meticulously merging that data into production. But what happens if a quality check fundamentally fails? Normally, the pipeline crashes and stops, leaving massive temporary tables eating up your expensive cloud storage budget. Airflow solves this elegantly with the new setup and teardown tasks. You dynamically designate your table creation as a setup task and table deletion as a teardown task. Airflow strictly guarantees that the teardown task will always execute, effectively cleaning up the database, even if the intermediate data quality checks crash and burn. Furthermore, using Airflow's native SQL column check operator, you effortlessly enforce that critical columns have zero nulls before data reaches your users. Look closely at the vital dotted line in this architectural diagram. We begin our DG with a setup task that provisions a temporary staging table, followed sequentially by loading our raw data. Next, we execute our critical SQL quality checks. If the checks successfully pass, we proceed to merge to production. However, notice the highly unique relationship with the teardown task. The teardown task dropping the temporary table is intrinsically and permanently linked to the setup task. Even if the SQL quality check fails heavily and halts the production merge, the dotted line ensures the teardown task is always triggered to clean the cloud environment. Let's tie all these theoretical concepts together with a powerful, real-time use case. Imagine your company needs to pull daily weather reports for the top 10 cities and strictly load them into a Postgres database to power an executive daily dashboard. Doing this manually is a nightmare. Using Apache Airflow, you construct an intelligent ETL DG scheduled to run daily. Task 1 uses a Python operator to make a REST API call to the weather API, utilizing the data interval start template variable to efficiently fetch only yesterday's weather. Task 2 cleans the JSON response using pandas and checks for critical anomalies like temperatures reading absolute zero. Task 3 uses a Postgres operator to run a precise upsert statement, loading the cleaned data securely into your database. By scheduling this resilient pipeline, the business receives highly accurate, automated weather analytics every single morning, completely hands-off. If the API is down, Airflow simply retries it. Here is the clean, end-to-end architecture of our real-time, automated weather analytics pipeline. On the far left, we extract the raw JSON data from the external weather API incrementally. This fresh data flows directly into our Python processing task, where it is parsed, cleansed, and strictly validated against our quality metrics. Once the data completely passes our quality thresholds, it moves downstream into the Postgres database task, where the clean records are securely upserted to prevent duplicates. Finally, because Airflow reliably schedules this entire orchestration every single day, the Streamlit dashboard on the far right is automatically populated. To brilliantly conclude our training, let's review the critical best practices for deploying Airflow ETL pipelines in production. The absolute golden rule of Airflow is idempotency. You must rigorously treat tasks equivalent to database transactions. This essentially means if a task fails midway and you manually rerun it, it should produce the exact same outcome without ever duplicating data. Never use basic insert statements in your pipelines. Always use upsert or merge to completely prevent data duplication. Secondly, strictly avoid writing complex processing code at the top level of your DG Python file. The Airflow scheduler evaluates and parses your DG files constantly. Top-level code will slow down your entire system. Finally, always leverage Airflow's encrypted connections and secrets management instead of dangerously hard-coding API keys. That wraps up our deep dive into Apache Airflow. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. This final logical map consolidates the core principles of a senior Airflow developer. At the top left, idempotency is king. Always carefully design tasks so that multiple runs yield the exact same, unduplicated results utilizing upserts. Moving to performance, you must keep your DG files incredibly lightweight by avoiding top-level execution code, and we highly recommend utilizing the modern TaskFlow API for clean Python scripting. Lastly, under security, never hard-code your credentials. Always firmly utilize Airflow's natively encrypted connections and external secret managers. By adhering to these pillars, you will build unbreakable ETL pipelines.